still set up, everything's still running, nothing has changed there.
Yes.
Sounds good. Okay, so go ahead and share. And I just wanted to talk a little bit about the scratch transducer. So when we've talked about the transducer in our previous trainings, we've talked a lot about how we've got the top plate and the bottom plate, and then the center plate. And the center plate is what moves up and down. When we apply a voltage to that bottom plate, we can pull it down. And from that, it is calibrated, and we can get accurate force and displacement data in the normal direction. Similarly, in order to scratch, what we did is we took two of the transducers and turned them on their sides. So that now we can also move in this lateral direction, right? These center plates can move back and forth like this. One of them is essentially a dummy. It's there because we needed something that would move, would push against. And the other transducer is calibrated. So just like the normal force transducer, we have also calibrated this one to have accurate force and displacement data. When we talk about the scratch transducer, one thing I want to talk about is how it's built. So if we take that transducer, sorry, this is the document I was looking for that I couldn't find. This is also always much easier in person on a whiteboard. We'll do our best here. One thing that's important to understand, actually, maybe we pause on this point until later in the training when it will make more sense. Trying to decide. Let's go ahead and continue. All right. So here is a rough image of what the transducer looks like. Right, we got our probe and our center plate. Hopefully this is making some sort of sense. I wanted to talk about what goes on in the lateral transducer. Okay, so there are two of these lateral transducers on either side of the transducer. Now, if you recall during the normal force training, what we talked about was that physically we can only apply a voltage to this bottom plate. So we can only pull this probe and this center plate down. We can't push it up. However, due to physical restraints on how this is built, we can actually control from either plate. The problem is we only calibrate to one, so we need to pick one. So you're going to have an imaging position for your transducer. Nominally, it's usually about 10 microns, 10 to 16. It's either positive or negative. Can you go ahead and look at your calibration screen for me? And on the left-hand side, there are transducer constants, and it says indentation access, and then it says scratch. And one of those settings should say imaging position.
Under what?
In the system calibration screen. Are you there?
System calibration. System general.
Yep. Yeah, so calibration, system calibrations, and then it's where we do our indentation access calibration. That same screen with all the transducer constants listed.
Okay.
And there should be constants for the scratch calibration, load scale factor and displacement scale factor. Do you see that?
Yes.
Okay, is there an imaging position listed?
Imaging position. Yes.
Okay, what is it?
Minus 9.1.
-9 what? Sorry?
0.9.
I'm sorry, what was the number?
Oh, let me share quick. Minus 9.9.
-9.9. Oh, you're sharing. Sorry. Got it. Okay. Can we call it 10 for the purposes of training as I'm explaining this?
Sure.
Thanks. I just wanted it to be relatively close to yours so that you could understand what was happening. Okay, so the thing is that we have, see, this center line. So I'm just going to draw this here, make it orange. So this is like the center line of the transducer, where if our our center plate is over here, it's under control of this plate, or if it's over here, it's under control of this plate. So basically, which side you're on is going to dictate which plate you calibrate to. And so you don't want to cross through this 0, 0 and switch control during a test because you're only calibrated to one. So for your purposes, you're over here at -10. And so that's your imaging position. So we're offsetting from the center point so that way when you do a scratch, for your system, I believe the maximum scratch is 15 microns. That is not 0 to 15. 0 to 15 would move the center plate from its imaging position of -10 to +5, thus moving it over to this other plate. What you need to understand is that it's 15 centered around 0. So it's -7.5 to 7.5 is your maximum range. And you're going to see this show up in the load function. So I just wanted to give us a quick introduction on why that exists. Are there any questions on that?
Last part, you said the scratch max is 15 micron?
Mm-hmm.
Okay, got it.
Okay. I'll have you go ahead and share your screen. Okay, so let's see. When we do scratch, almost everything else still has to be correct. So my question is, have we still done all of the other steps? Did we do our daily, what are our steps? First is the hardware loaded. I assume that the transducer is on, given that the system is running. The second is, did we do our daily indentation access calibration?
Today?
Not today, so let's go ahead and let's get that done too. Okay, so it actuated, it went, from 0 to about 4 microns. We're fitting from 0.8 to 3.6. The red line of travel looks appropriate. There's a small noise that is standard for this system. But there's no discontinuities or large random noise issues happening. The blue line of travel follows well. So all of this looks good. So we can go ahead and click yes, and then we can close this plot. I think your yes is on your other screen, that pop-up.
Yes.
I remember that from last time. Okay. And are all of the samples currently defined?
Yes.
Okay. And is our tip to optic calibration accurate?
Tip to optic. I think so.
Yeah, so so we did it last time we did training. The only time the tip to optic is updated, right, is if we move the tip or the transducer, which I'm assuming has not happened. You guys didn't change probes on me or anything.
No.
So it should still be accurate. So good. And then my final question to you is, Usually the question is, do I have an accurate tip area function? For Scratch, do I need one is the question. And what that question is really asking is, what does the tip area function give me again?
The tip area function. I think the tip area function gives us a good beginning reading of where 0 is.
Rezeroing is necessary on all data files. That is not, and so therefore it was part of us performing the tip area function calibration, but it is not the same thing. Those are two separate steps. I guess my question is, why do we do the tip area function at all? What does that give us? What information?
Kind of define X, Y, and Z.
Are you thinking of the tip to optic calibration, the one that we're currently looking at, which gives us the offsets?
That one I think is my nose is a little messy.
Yeah, so just backing up, so tip to optic calibration is what gives us the offset between the focal point and the tip in X, Y, and Z. That is true. That is not the calibration I'm asking about. I'm asking about the tip area function. Do we recall discussing the tip area function as a theory? Why it's important?
Tip area function. To correct the efficiency, what I called, like the system has a like efficiency or a rate, not a ratio.
Let me back up. What are you typically testing when you do an indent? What results are you looking for from that material?
Hardness and the Young's modulus.
Yes, hardness and reduced modulus. Keep in mind our system reports reduced modulus. If we remember, what are both of those things dependent upon?
What are both them impended upon?
Right, so in the equations, hardness is the maximum force divided by the contact area. Reduced modulus is the stiffness divided by the contact area, or the square root of it. Contact area. Do we remember what contact area is?
What contact area?
So contact area is how much of the probe is in contact with the sample at the time of the indent, correct?
Yes.
So what we did, the tip area function gives us the relationship between contact depth and contact area.
Okay.
So normally that needs to be done so that when we do an indent into one of our samples, we can go, when we ask the system to do the calculation to give us reduced modulus and hardness, we know that those calculations will be correct. If your contact area is correct, your tip area function is correct, then you will get proper results. What kind of results do you think we're going to get from scratch testing? What are we looking for if you look at scratch testing?
Like
Let me
resistance?
Yeah, you're looking for how that tip slides across the sample surface. So the most common examples are coefficient of friction, where you have a really big probe that slides across the sample and you're looking at the friction between those two items. The other really big example is the critical point of delamination. So that's where you try to have plastic deformation to dig into the sample, to wear away some of it so that you can see when you like break through a coating or some other, an interface of some sort. So those are the two major ones. Neither of those are looking for hardness and modulus results. So for scratch testing, you actually don't need a tip area function.
Okay.
Does that make sense why?
I guess it does not really need, well, if the tip area function is like calibrate the probe depth and then the contact area, I guess the scratch also indent it and then scratch it.
Right. So we're not testing for hardness and modulus anymore. We're testing something else.
I guess. Yes.
Yeah. So the contact area is no longer needed. Okay, so what I'm trying to get at here is that when you're setting up the instrument for scratch testing, the question is my tip area function accurate? The last one that we have to answer before we can begin testing on our samples. It's a little bit tricky when it comes to scratch because the answer is it doesn't matter. I'm not getting hardness and modulus results. So we can go ahead and say, okay, that's good enough. So all that being said, why is it so dark? Are the lights on?
No, I turned it off.
Oh, you turned it off. Okay, good. I see. Okay, so we're currently on the fuse quartz standard. For training purposes, I don't want to scratch on fuse quartz. You have one nice Berkovich probe, as far as I know, that we have spent a lot of time calibrating so you can get correct hardness and modulus results. We're going to scratch on the aluminum standard instead, in the hopes that it will not blunt the probe. And we're only going to do 1 or 2 scratches. So let's go ahead and focus on the aluminum sample. Do you remember how to get there? How to get the optics to go there? Yeah, actually, you want to right click inside of the sample boundary. Can you move south a little bit? We're kind of close to the edge of this sample. Sorry, south, as in like down in Y, negative Y. Oh, I didn't know that the software did that. You can go ahead and click that center point, and you can click remove point. Delete point.
Oh, no.
Nope, 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 nope. There's delete point. Sorry, the second from the bottom. Yep. There you go. All right, can you move down in negative Y? Yeah, okay. Our sample zones, I think, were a little messed up when we updated the software, but we're pretty close. Okay, we're over the aluminum standard. Okay, so scratch testing. We did our indentation access calibration, and everything else is well set up. Our samples are well defined. We don't need a tip area function. Everything is good to go there. So let's talk about scratch testing. If you go ahead and go to the system calibration screen, the system calibration screen. Yep. Let's go to system general. Good. So here we have our transducer constants. We've talked quite a bit about the indentation access calibration constants. Similarly, for the scratch axes, we do have a load scale factor and displacement scale factor. These are the relationships between load and applied voltage and displacement and measured signal. So each transducer has a unique scratch axis calibration as well. And then there's also an imaging position, which we just talked about. That is the offset in the scratch axes. We also have a daily scratch axis calibration. So this needs to be performed every day you're doing scratch testing. So you can see here that similarly to the indentation axis calibration, we have the electrostatic force and plate spacing. There's also a displacement offset, which is new for the scratch axes. But we can go ahead and click calibrate under scratch axes when you're ready. Good, and a lot of things are happening here at once. So I want us to note that in the upper left-hand corner, where we have the displacement, actuation, and sample force is a new setting. Do you see where I'm looking? Actually, maybe what if I take control here so I can at least point? Oh, can you give me control? Oh, there we go. Thank you. So here, right, we've looked at this before, this displacement, actuation, and sample. This is the sample force we've been using to determine if we were in contact or not during imaging. Now, there is an X parameter here. You can see it's moved to that imaging position of negative 9.9 as expected. It also updated your mode to scratch mode. So we turn on the scratch axes and it immediately moved to the imaging position. It's a good sign. It means it's actuating well, it's moving well. So that's what we're looking for. When you click Cal Air Scratch, it brought you into the scratch load function screen, which we'll talk about at length. But basically, you just get another graph, right? We're used to this normal force versus time graph as a load function. Here now we have also lateral displacement and time. So for the Cal Air indent, what we're going to do is during the indentation axis calibration, all we do is actuate down and back. And then we calibrate to the springs, knowing that the force felt should be 0. Similarly, here for the scratch axes, we do not move in the normal direction. And instead, if we walk through this calibration, right, it moves back 5. That's that first leg where it goes from in lateral displacement from 0 to negative 5. Then it holds, and then it goes from negative 5 to positive 5, holds, and then it comes back to 0. So 0 to negative 5, negative 5 to positive 5, so 10 micron scratch here. Hold, and then back to 0. So what we're going to do is during this long scratch, we know that the force felt should be 0. We're in the air. We're not scratching against anything. Just like in the normal indentation axis calibration, it's going to take that data, the spring data, know that it should be 0, and correct the electrostatic force to make that true. Oh, good? Is that a question? Sorry. Okay. So whenever you're ready, you can go ahead and click Cal Air Scratch. And we're going to get 3 live graphs. They are going to look a little bit different. Okay, so you can see here we get X force versus time, Z force versus time, and Z displacement versus X displacement. I'm typically always looking at this last graph. Is it doing what it's supposed to be doing? And it is. It's not supposed to be moving in Z. Started at 0x and it went to negative 5x. Now it's coming forward all the way to positive 5 before it will come back to 0. So watching the displacement lets me know that it's actuating, which is what we want to see, right? If it's not moving, there's something wrong and you need to call me. All right, so it went out to positive 5. And now back to 0. Now we also get our first view of the scratch analysis screen. In this screen, you get 4 graphs. You get lateral force. Let's go clockwise. You get normal force, normal displacement, lateral force, and lateral displacement. Now keep in mind we had we had programmed the normal force and the lateral displacement. So my first thing I always do for every scratch, whether it's a Cal Air scratch or any standard one, is did it do what I asked it to do? And what I asked it to do was have 0 force in the normal direction. And then I asked it to move back 5, forward 10, and then back 5. So did it do both of those things?
It did.
It did. So what we're going to do is we're going to go ahead and click yes here, and it's going to take this center part and this lateral force, and it's going to calibrate that to 0. So when we do so, a couple things change. You see now from this screen, we only have this segment selected. So we're going from 8 seconds to 38 seconds here. So that's that center scratch from -5 to +5, which we can also see in this lateral displacement here. How we judge the calibration is based off of the lateral force. What we typically like to see is it's centered around 0 and the spread be roughly 10 micronewtons or below. It looks like that's mostly true here. We're offset a little bit. That's pretty typical when the transducer first goes into scratch mode. You're turning on a bunch of circuit boards. So there's some heat there, so sometimes we have to wait a little bit and then run another calibration. But this one actually looks pretty good. Overall, this spread is about 10 micronewtons, which is fine. There's a little noise right here, but without being in the lab, I couldn't tell you precisely why. I'm guessing somebody walked by or a door opened or closed maybe during that calibration. Does that sound correct? Or is it pretty quiet?
I mean, I'm around.
I'm sorry?
Standing right next to it. I said I'm standing right next to it, and another student just walked by.
Yeah, so that could lead to those kinds of things. So overall, I don't see anything here that would make me suspect that the transducer is poor.
Okay.
So this scratch axis calibration needs to be done every day that you intend to do scratch. It should also only be performed after the indentation axis calibration, since we are also using the normal force to calibrate too. Just making sense? Any questions on the calibration part?
You said the lateral force, as long as like limited in 10 micronewtons, should be good, right?
Yeah, that's like a rule of thumb. What I'm looking for is I want to make sure there's no like weird big, like there's one little spike at the end there, but I'm looking for like a sustained long spike or, just like a lot of noise. Yours is very constant, it's very, I think that is just the noise level of your instrument. So roughly 10 micronewton peak to peak.
Okay.
I have one question.
Mhm.
Do we need to normalize this or reduce this noise?
I'm not sure how you would normalize it. I guess
Normalize means will it add up to our error in your final calculation?
the noise will be, yes. I mean, your system, like we talked about, it's different than the 950. The anti-vibration system is completely different. So it does have a much higher noise floor than your 950. And yes, I mean, that is something that is going to may or may not impact your measurements, may be present. But usually by the time you get in contact, that dampens a lot of this noise out. Keep in mind that we're in the air where a lot of those vibrations can come through. So it typically, you don't see it as much in your data as you do in the air.
Can we get some dampers separately and install below the system so that it can minimize the vibrations? Will that help?
Right. So the answer is maybe. It's really hard. Anti-vibration systems are difficult to design, and once you start stacking them, it can become even more difficult. So anti-vibration systems, airtables, they don't just dampen everything from 0 hertz up. There is actually usually a peak. They actually amplify typically below whatever their peak is, and then they dampen after that. And how well they dampen after that is completely dependent upon whatever anti-vibration system you're getting. So you can add an anti-vibration system. Whether or not it will help is difficult. I have seen people successfully add active anti-vibration to these systems. Just a little unit that goes around it, sits on. Those I haven't seen a problem with. Airtables can be, more difficult, and then you also have to consider the the cable length. You don't want to strain the cables. So there's a lot of considerations that go in there. Where is the instrument? Is it sitting? Are you guys on the second floor? Do I have that right?
We're kind of like on a hill, like from
That's
one
you
side we're on
guys.
the second, from the other side we're on the ground floor.
Well, for me, from an instrumentation perspective, ground floor means sitting on the ground, which is not the case here. It sounds like if you are part of the second floor from the other direction, that means that there is, you know, if you think about something sitting on the earth, right? There's all this earth that is very inert and it dampens out. Versus if you're on a floor with a room below you, you're basically sitting on a drum head, which means that vibrations travel much more easily through the floor and into your instrument. So things to consider. If you can move it to a quieter place, that might be better. We need to talk about that though, because you're under warranty. That's the other thing is that I'm not sure, you know, it would depend on what you wanted to add. I would want to talk about it before you did so. So if you wanted to look at options, you certainly could, and we could discuss.
Okay.
Does that answer your question adequately?
Dr. Nico, your question is answered.
Yes.
Okay. All right, let's go ahead. And the best way I found to train Scratch is just to talk about the load functions because they're not necessarily trivial. So let's go ahead and let's go back to the Perform Test tab.
Performance. No.
Let's go to the Perform Test dropdown.
Second tab.
Yep, second tab from the top, Perform Test.
Oh, my bad.
No problem. Yep, and then switch to Scratch. Perfect. And then go and let's open up a standard load function. So go to the hamburger menu for me. And standard load functions. And let's start easy. Constant load Scratch only. Good. Okay, so the first things that we note is that your lateral displacement, for the lateral axes, you don't get to choose. You only get displacement. There is no load control in the X direction. For the normal direction, you technically get a choice. You could do displacement control, but I encourage you very much not to. The reason is that people think that the displacement of the tip into the sample, if they do displacement control, will also be constant. And that's not necessarily the case. So this is a little tricky, but we have to think about physically what's happening. When we displace the tip, what's really displacing is that center plate of the transducer. So the measurement is inside the transducer. It says move 2 microns, so it moves 2 microns inside the transducer. That means during indentation, that's going to be the same thing, right? Because you touch the sample surface, then you go 2 microns into it. However, when we begin to talk about Scratch, what that means is that it goes 2 microns in, and then it scratches inside the sample or along the sample surface and then unloads. Now, if the transducer and if the sample is perfectly flat, those two numbers will be the same. We're talking about nano indentation, things are never flat, so it's going to have some tilt. So if I do a 2 micron displacement and then scratch, I'm no longer constant inside of the sample, I'm constant inside of the transducer. So people often try to use displacement control, but I do not recommend it. It is not doing what you think it is doing. So we typically recommend to leave your normal direction in load control feedback.
Okay.
Okay. Let's see, what else have we got? The system has a maximum force in X of 2 millinewtons, but there's nothing to stop it. So you have to be smart and you have to think about what you're testing. People often try to go really big on scratches, and that results in typically very blunt probes and poor data, because if you go too far, you can actually kind of get stuck in the material, and then instead of scratching, it will just lean and then kind of skip along the sample surface. So scratch is a very, I mean, all nano indentation is very physical. But with scratch specifically, you have to be very careful and pick parameters very carefully. So let's go ahead and walk through this load function. There, we'll go segment by segment. So this first segment, this 0 to 5, my normal force is doing nothing, but I'm moving -5 in x. During this next segment, my x is doing nothing, but I'm loading into the sample. During this next segment, I'm loaded into the sample, but my normal force remains constant while I scratch. So then I move to the +10. Then we stay at that +10 while we unload to the sample surface. And then we come back to 0 in the lateral direction. So this is move backwards, load, scratch, unload, move back to 0. Pretty straightforward. Are there any questions about this one in particular?
No. So kind of. So here, the peak force here now is 0. So identify this.
I'm not sure why that's set to 0, because that's not what it looks like to me. That looks like a bug. I think what happened is, you remember during our calibration, there it is. It just didn't load correctly the first time.
Okay.
So yeah, in this case, it's 1,000. So you can see the normal force goes all the way up to 1,000 here. Okay, the next standard load function is where things start to get a little bit more complicated. Here, this should look very similar, right? This part, we're loading while we're constant in the x. We're holding in z while we scratch. We're unloading and then moving the scratch back to 0. But there's an entire 20 seconds of test before that. This is how we get our tilt correction, so that we have accurate normal displacement results. And I'll show you what this looks like in the post-analysis. But you can see here that for the first 20 seconds, we are 0 in the normal force. And here, so we're tracing the sample surface, we're in contact, and we go back 5 microns, forward 10 microns, before we load into the sample, do the scratch, and unload. And the purpose here is that this way we have a measurement of the sample tilt before we perform the scratch, so that we can correct our data. Does that make sense? Any questions there?
Well, sort of. Let me ask this question. So on the top, as you mentioned, this is the one that scratch with the tilt function. So the on the above is the normal force, as you mentioned, the first 21 second. It just touched it, right? And then scratch and unload and back to 0. So for the lateral placement, so if the first 21 second is not, it just basically touch, like before touching it, so why it does look like this?
We need, so in a perfect world, all samples are flat, right? That's not true. There's some tilt to them. And so the goal here is that we trace the sample surface before the scratch, because the displacement of the because that way when we do the scratch, we can correct for this.
Okay.
I think it will be a little bit more obvious. Let's go ahead and perform it, and then we can take a look at it. So let's go ahead and let's decrease this force drastically. So the problem with scratch training with a Berkovich probe is that we run the risk of blunting your probe. So for the purposes of training, I typically do very, very, very light scratches to prevent damage. So let's change that peak force to 200 micronewtons. Perfect. And you can see now how this is updated. Oh, we should talk about this really quick. Sorry. Down below, we also have begin lateral displacement and end lateral displacement, as well as max and min. So the max and min change, if I do the 7 here, you can see now it's changed overall. Versus if we do begin and end, that is for this specific segment. So this one goes from 5 to -5. So let's go ahead. Yeah, so you can change the scratch length that way. So whenever you're ready, you can go ahead and click Perform Scratch. Start. So everything here should look pretty similar. It moved up to the Z fly height. It's moving over in X and Y to get the sample underneath the probe, and then it will approach the sample surface. Ah, can you go to the sample navigation screen for me? Just click there. Maybe not. Is it frozen? No. So this is going to take a very long time because we forgot to do our quick approach. See how it's Z contact is 0. So this approach is taking forever. So it's actually going to be faster if we click stop, do the quick approach, and then do the test. So I'll have you go ahead and do that.
Well, the probe is almost touching it.
It is not. It will take a very long time at this rate.
Okay.
It looks like it by eye, but from a nanometer level perspective, it's going very slow and it still has quite a ways to go.
Should I wait for it to stop and then quick approach?
Yes. Yeah, we should wait till it gets back to the optical position because quick approaches can only ever be performed from optics. Okay, now go ahead and do a quick approach here.
So for this one, we just identify like how long it's gonna scratch.
I'm sorry?
I guess for this one, we just define the time, like how many seconds it gets scratched, right?
And how long?
And
By
how
this one,
long,
you
like,
mean what length? Sorry, that's yes, you are correct that we do it how long and how long, meaning both the time and the distance.
yes. But we just define the time and not the distance, right?
We can change the distance. I use the defaults, but you can change them like I showed with that 7. We'll take a look at it
Okay.
when the quick approach is done. Yeah, we'll play with it a little bit.
Okay.
No, good question. Good. Okay, we just made contact. So the quick approach. Now we'll come back to the optical location.
I was wondering why after a quick approach it doesn't say, just disengage as.
I'm sorry, can you repeat the question? I thought I understood,
As
but
I was
I don't think I
wondering,
did.
as I was wondering why you just go back to the optical position after approach. Maybe it should will make it easier if we just like go up a little bit in the Z height instead of going back all the way to the optical position.
Because it did a quick approach, which is completely separate than doing a scratch. So the system, if you remember from our discussion regarding the tip to optic calibration, it needs to have a contact height for the sample, which means the tip has to come into contact with the sample at least once. If it does not, so let's back up. How does an approach work, right? You're looking at the sample surface and you say, go do a scratch here. So it lifts the tip up, comes down, and brings it into contact. If it has contacted the sample before, if this last contact height, Z contact, is correct, then it knows that it can go really, really fast till it's really close, and then it can go slowly and very gently touch the sample surface before performing the test. That's very important that it's very gentle before performing the test because we don't want to cause any plastic deformation. If you do not have this Z contact height, if it is 0, the system is unsure where that sample height really is. So it starts the slow approach all the way up here. And then it goes click, 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 one at a time, very slowly until it finds that sample surface because it doesn't want to leave any plastic deformation. That's what was happening to us. And it takes a very long time. So what we did is we added a quick approach where the quick approach does not have a test attached to it. The quick approach's only job is to get the tip into contact with the sample once to make sure that it has a last contact point so that future tests can be faster. So we did not perform a load function. All we did was a quick approach to update that Z contact point here. So now we will have to go back and do the scratch. So now it lifted up. It's moving over in X and Y. Now it's moving to the Z safety height, which is much closer, so it's going to move a lot faster here than it did before. And it found the sample surface. Now it's doing 60 seconds for motor settle time. "45 seconds for piezo settle time." And then we get our controlled single scratch drift. Oh, was the drift correction on the other screen? Is that why I couldn't see it? Okay. Well, in any case, we get 3 live graphs. So we've got x force versus time, z force versus time, and z displacement versus x displacement. So here you can see we went -5 in x. Here we are lightly tracing the sample surface. It's currently loading into the sample. You can see that z force increasing. Now we have some x force happening as we scratch along the sample surface. The scratch is complete. It's unloading from the sample. And now it's going back to this x is equal to 0. I know that probably looks like gibberish to you. It will make sense soon. So go ahead and save this anywhere you'd like. We can call it a 200 micronewton AL scratch. Micronewton, not milli, but yeah. Perfect. Okay, so now it's withdrawing from the sample. We shouldn't like do anything while it's moving, but we can at least talk and look, right? So again, my first question is, did it do what I asked it to do? And again, we had programmed the normal force and the lateral displacement. So those are the two graphs I'm going to look at first. And it looks like it did. It held at 0, loaded, held at 200 micronewtons, and unloaded and went back to 0. On the lateral displacement, it also did what I asked it to do. It went back to -5, went to +5, held. This is where it actually performed the scratch. It held, and then it came back to 0. So I'm going to wait for it to finish here before I make my last comments. So we know that these are correct, and then our lateral force was also measured correctly, but this normal displacement is difficult. So if we look at this graph, I'm going to grab these bars, and I'm going to look at this segment first. So this segment, you can see that the bars are updating on the other graphs as I navigate. Right, they match here and they match here. So that tells me what segment I'm looking at. So during that segment, that was when my normal force was 0, so I was lightly tracing along the sample surface. And then we also have this lateral displacement from -5 to +5. I'm looking at the normal displacement, and I can actually look here to see that the relative difference there is 155 nanometers, which is significant and also not what we want to see. So that's the tilt. And so I'd like to take the tilt out of the equation. So I'm going to go ahead and take these 2 points. Those 2 points. It's more accurate. And what I do is I'm going to go ahead and hit tilt correction, and it's going to take whatever is in between these 2 bars in the normal displacement and say that should be 0. That is the tilt. And then it will apply it to all of the data in the normal displacement to correct for it. So I hit tilt correction, and it made this 0 to 0. So now we get a more accurate normal displacement. So we can click through and look at these different scratches, see what the displacement looked like here. So this is during the actual scratch in contact with the sample. You can see that we have our normal force. We have a pretty constant lateral force too. Looks like we're getting some bumps in the normal displacement. I'm wondering if we had some buildup from the aluminum. Yeah, so we can look at it as a whole and pick certain segments, or you can actually just pick which segment you're looking at. It's like this is the segment where the scratch actually occurred. The other item that we can look at is the friction. So we can get this separate graph that gives us, did it pop up on the other screen?
Yeah. That's my mouse.
This is actually a really nice graph, but you get 0.3, right? The friction is just the lateral force over the normal force. And so you can see this calculation here over the course of the scratch, or over the course of this portion of the scratch. Right, if we look at all of it, and then look at the friction, it's going to be some nonsense when it's not scratching. Oh, sorry, can you bring it back over? Sorry, I might have clicked something there. So here is where we were looking before, but this is all where it's at 0 force. So of course it doesn't make a lot of sense, but here's where we're looking. And just for curiosity, well, that might have been it. I'd have to check. I'm not sure how close we forgot to take an image before we did the scratch, so I'm not sure which one of those is real or if any of them are. But yeah, that's a constant load scratch. You have any questions about this? I can reload it so you can try the tilt correction for yourself as well.
So what does the tilt correction do anything to click it?
Don't click it.
Oh.
So go ahead and reopen the file. So here's the uncorrected area. Now, which segment was the tilt correction? What segment will give us the sample tilt?
Tilt. Yeah.
What is the definition of finding the sample tilt?
No, sorry, this is a scratching.
That's the scratch, yeah. That's when we were loaded into the sample, right?
Uh-huh. I guess this area?
Yes. So that's when we're scratching, or we're not scratching. We're tracing over where the scratch is going to be during that segment. So go ahead and get your 2 bars on that segment, across that segment. Yeah, it's a little unwieldy. It's closest click. So not that section, but rather this section, right? Because this section is where our force is 0, but we are moving laterally. So we're just tracing that sample, right? So how this works, maybe this will help, comes down and into contact. It goes back -5, goes forward to +5, then it loads, performs the scratch, and then unloads. So this segment, when it's doing this little tilt trace, that is what I want to look at. So hopefully it's constant, but this is where we should be looking, right? This segment.
I have one.
Mm-hmm.
The first segment is also a little bit variation that we can see in the normal displacement. So it is coming down the first segment.
Do you mean the force segment or the normal displacement?
Yeah, the first segment of the normal displacement.
Yep, so that makes sense if we think about the sample tilt, right? Because we landed here, and we're landing in the center of where our scratch will be. So I have to move back 5, so it's going, let's do this the right way. I have to go back 5, so it's going to go down, and then it's going to scratch forward, and it's going to go up.
Oh, now I got it. Yeah, that makes sense.
Good. Thanks. I always feel so silly, but doing it physically is, I think, the best way to really think about what's happening during the scratch.
Yeah, that's pretty much, I make that. Yeah.
Good. Okay, so you found the segment, right, where we're scratching along where our scratch will be, or we're tracing along where our scratch will be. So my question to you is, should there be any change in the normal displacement? If I want to correct for, then maybe that's not the best way of asking that question. So right now, because I have sample tilt, I cannot trust the change in normal displacement during my scratch, right? Any tilt is going to also be in that data. So if I want it to be accurate, I need to correct for that tilt. So we do so by selecting these 2 points with our cursors, and then only then can you hit tilt correction, because what that does is it takes the normal displacement between the 2 points and it says this should be 0, and it flattens it. So if you just hit tilt correction without choosing those points, you're changing the data strangely. It doesn't make sense. You have to pick where you measured the tilt. And we measured the tilt here because it has 0 normal force and we are scratching along the sample or tracing along the sample.
Okay. So not too crack?
So yeah, the reason I had this one moved in a little bit is, do you see how there's like this bump and then it goes down? I think that that's artificial and I want a better measurement. So I think that this is a more accurate representation of the sample tilt than going to the other side of this bump. So that's why I'm headed there. But yes, now you can hit tilt correction and it's going to make these 2 at the same lateral normal displacement or very close to it. So it's flattened this out. Now there is some bumps here. Aluminum is a weird sticky sample, so we're probably getting a little buildup. But you can see that that's what we've done here. And now we can be much more confident in our sample forces. So like here is where we loaded. And then as we started to scratch here, right, this is our scratch segment. It looks like we like pop back up. So like we probably loaded, and then as it scratched, it popped out of where that the peak displacement was and slid, and then it probably dug itself in a little bit. So the aluminum's a little bit of a weird sample to be doing this on. Usually it's a little bit clearer, but hopefully that gives you an idea of what we're looking at.
Mm-hmm. And after the two function, the friction is okay. And we say if we want to see the low.
Friction is just normal force, lateral force over normal force, so the displacement doesn't matter for that.
Okay. Okay.
Okay. Is this making sense? Because I'm about to make it weirder.
Yeah.
Okay, let's go back to the Perform Test tab. And I want you to go to the hamburger menu. Standard load functions. Constant load with tilt retrace.
Ooh.
So, yeah, exactly. Weirder, right? Hopefully the beginning looks a little bit familiar. So here, 0 normal force for that first 20 some seconds. As we pull back, then trace along the sample surface where our scratch will be. Where people get confused is these little steps in. But really, you know, we look at this and basically we're still at 0 micronewtons. So it traces and then it comes back just like a little bit. Then it loads into the sample and then it performs a scratch. And the scratch length here is only 6 microns, 6 microns. So that it's only taking up part of this area. So then we scratch while we're loaded in, then we unload, then we go a little bit further. And then this is again the same. It's very similar to this first one, only now when you're retracing over the scratch. So you can see how the normal displacement changed pre versus post scratch. How deep is it? How much material did you take away? Is it constant? Okay. And then we get into, so basically, I showed you this one, constant load scratch. Never do this one. You always want to be able to correct your sample tilt. So typically I don't recommend you use that one. Instead, I recommend you use either constant load scratch with tilt or with tilt and retrace, depending on what information you want from the rest of the test. And then we can add a variation on this where instead of having a constant force, we have a ramping force. Where again, very similar, right? 0 micronewtons, we pull back, we trace over the scratch location. The only difference here is that there's not like, oh, we're going to stop and load. We're loading while we're scratching at the same time. Hold, unload, comes back to 0. And also see it with tilt and retrace, which really looks crazy. Is this making sense so far?
Yeah. So, what do you call them? I guess that the retrace one kind of have like a dynamic force. Like what's the right? So for the scratch, so let's say for this two, the scratch with tilt and scratch the low with tilt and retrace. What different information this two can give?
What's the difference between with tilt and retrace?
Yes.
this last segment, this part. Basically, if you don't have retrace, that part doesn't exist, right? You just do the little pre-scratch, you do your actual scratch, and then you're done. This goes again. So this is, we look at with tilt, it only has this first part where it traces. So in that first part, it's tracing over the sample surface to see the normal displacement change as a function of the lateral displacement so that we can correct for it, right? Then this is where the actual scratch occurs, either with a ramping load or with a constant load. And then that's where this one ends. Basically, you unload and you come back to zero. This is it just coming back to zero in both the normal force and the lateral force. When you add the retrace segment, you get this extra portion, this extra 20 seconds at 0 micronewton. What's happening here is that you're doing this again, only it's after the scratch. So you're tracing over where the scratch is. So if you think about, you trace so you can do the tilt, then you do your scratch, and let's say you're really trying to like dig out some of the material, trying to make a deep well for some reason, whatever you're testing. Then after the scratch is done, you unload, but then you trace along it again, and that tells you how deep that trough is. So then you have the normal displacement before and after the scratch to tell you how much that normal displacement changed, to tell you how much sample you wore away.
Is that force?
Or
Like,
go ahead, sorry.
Is that force constant or dynamic?
You cannot do both scratch and dynamic at the same time. So this is 0 micronewtons. It's really, it's 2 micronewtons. It's the contact force.
Okay.
You guys don't have dynamic either. There is no dynamic testing on your instrument.
No.
This is just, it's just tracing the scratch. That's all it's doing. It's just measuring the normal displacement.
Okay.
Maybe I'm misunderstanding the question about dynamic. What do you mean by dynamic?
So, like, is the force goal, like, say, like, keep increasing until, like, 200?
Which force?
Like, for example, earlier when we did this, so once the probe like indented and it performed a scratch with this 10,000 micronewton, right? So with the retrace function, well, never mind, the force is the same. It didn't change.
Yep.
Okay.
Yep, you're just adding this 0 micronewton section here.
Okay.
You're just adding the retrace segment. You're retracing the scratch.
So for the retrace, now for this one is like approach, load, scratch, unload, retrieve. So for this one, it's like a back, like retrace like back and forth, and what's this section? I guess is get approach to the.
It's so if you think about the scratch, what you're doing there is you're overshooting it. So if this entire thing is 10 microns, is -5 to +5, what it's doing, this is a terrible example of this, but it's landing here, it's pulling back -5, it's going forward to +10, and then it comes back just a little bit, and then it does the scratch here, and then it comes out and it goes over here, and then it does the retrace. And the reason for it being offset like that into the center is so that you can get information about the end of your scratch. If you're going to retrace on the scratch that you made, you want to see when it goes into the scratch and when it comes out.
Okay. I'm still a little confused about this part.
Which part? Can you point to which part in particular?
like the retrace part, why this like lateral, like what is lateral displacement?
That is the X movement. That is the actual. So the transducer can move both in normal and it can move laterally. So the normal we're describing on that top graph, and then the lateral movement is what we're describing on the bottom graph.
Okay.
So it's the lateral displacement of the probe. It's the act of moving the probe laterally to make a scratch. Right? An indent is just up, down. To make a scratch, you have to go down and then move and then come back out.
Okay. Hello. Okay.
You can see the segments match to tell you what it's doing both normal and laterally when you click a segment. Right. Here it's showing you it's at 0 micronewtons here in the normal direction while it's laterally displacing. So that means it's just tracing very softly along the sample surface.
So after you try, like you retrace it back to the scratch?
Yes. Yep. You want to see how deep it is. You want to see what remains. You want to see how you change that sample.
Okay. I guess this will give you like the depth or something?
Yes.
Okay.
Yeah, that's what that information would tell you.
Okay. And then the ramp load.
Yes.
So the ramp.
So ramping refers to that segment that you just had highlighted. Yep, this segment. So what that means is that the force is not constant during the scratch, right? Because it's happening, this is the scratch segment. So as you're scratching, you're also increasing in load. So if you think about it, you're.
Okay. So I guess earlier that's what I heard. Like, so that's what I meant. Dynamic force. It's not constant force. The force is increasing.
Sorry. Dynamic is a very specific term for us from the marketing perspective. Dynamic meaning an oscillation. But yes, you are correct. It is changing as you load. Yes. Thank you for the clarification. I'm glad we stuck with it.
Okay.
Yeah, so that's used for like critical points of delamination. If you want to see how much force you have to load up on something before you can break through like a coating, right? Right now, everybody's carrying around glass in their pockets that we don't want to get scratched up. So you can see how having a coating and testing that coating to seeing how much force on that coating you would need to delaminate it would be important to manufacturers. That kind of example.
Okay.
Sometimes people also use the retrace segment. You said it very well earlier when you said, "Oh, it's to see the depth of the scratch," right? This segment. That's what that tells us. Sometimes people will use it to see that the depth is 0. What I mean by that is that we've talked a little bit about critical points of delamination. I think that's pretty obvious. But then there's also friction. And friction, by definition, when you test friction, you shouldn't leave any deformation behind. You're testing a sample to tip interaction, and you're trying to see how that tip slides along that sample surface. So people will sometimes do this when they test for friction as well, to make sure that they don't see any depth.
So
which I think brings a. Go ahead. No, please. This is good.
the scratch test will the end result or the data we get from the scratch test is just a friction.
Well, you program your normal force and your lateral displacement, but then you get lateral force and normal displacement. So you get to learn about how much that force, wore on that sample, or if anything interesting happened, like a critical point of delamination, by looking at the lateral force, and you get to look at how you wore the sample using the normal displacement. So you test quite a bit with Scratch. I actually, in our shared folders, was a document called The Basics of Nano Scratch Testing, that I highly recommend you read through real quick. It kind of goes over all of this again in more detail. Well, it shows you examples at least. But no, there's a lot more information to get out of scratch testing than just friction. Friction is just one type of scratch test.
Yeah, I saw it.
Sorry?
I saw the document.
Ah, good. Yeah. It's a nice little read. I think it's 2 pages. It has it's a nice summary, I guess is how I would put it.
Okay. Basic scratch. Okay. 9 pages.
Okay, maybe a little longer than I thought. Maybe that was before I put data in it.
Okay.
Also, friction coefficient, where you can do a constant load in 2 directions. I do want to talk a little bit about directionality. So if you look, let's see. Sorry, are there any other questions right now about what we've already covered before I launch into another note?
No.
I want to talk about directionality. Oh, sorry. Was there a question that I missed?
No.
Okay. So I am annoyed at the system because it labels your axes as an x-axis. I think that was just arbitrary, but if you think about the transducer, I told you that there are 2 extra transducers attached. You know how the transducer makes a little U-shape, little black U-shape?
Yeah.
The transducers are in those ears. And the transducer slides onto the system left to right with the ears facing you. What that means is that you're actually scratching in the physical Y direction. Does that kind of make sense? Can you see physically how that would work?
To be honest, on the stage, X and Y looks confusing.
Well, think about it as a cardinal direction, right? If you're standing in front of the instrument, Y goes this way, X goes this way. Just ignore the stages. They don't matter. It still measures in X and Y.
Okay.
So what I'm saying is that the transducers that make scratching possible are in the ears of the transducer. Can you see those?
Yes, hold on. I see. Sure.
Yeah.
Oops. Yeah, the transducer will kind of look like this, like if right in front, like if you're standing in front of it, it's just right in front of you like this.
Right. So you can only move between those. So it's moving this way. The tip is.
Yes. So it's in Y.
Right. In the cardinal directions, it's scratching in Y, even though it's labeled X here. And I bring this up because I have had customers who have a directional sample. At a macro level, think of have you ever touched velvet?
Velvet.
Trying to see if I have.
No.
But a material, velvet is a kind of fabric. And if you go over it one way, it sticks up different than if you go the other way. And it also is different than if you scratch this way. So that's why I think it's important for you as a user to know that it's really scratching this way. So that you can, if you need to orient your sample. If it's a bulk sample, who cares? But this nuance does become important. Even if you don't remember the exact nuance, what I want you to remember is that there is nuance if you have a directional sample, and then you call me and we talk about it again really quick.
Okay.
This also comes into play when we talk about the different kinds of scratch load functions. When you have a constant load scratch, we're going from -5 to +5. But as soon as you start adding that tilt direction, it goes the other way. Now, this is arbitrary. You could set it up the other way. But again, if you have a directional material, if you're scratching this way versus this way, you could get different results.
Okay. Yeah, thank you for that.
Yeah, the other thing to bring up here, do you have any other probes besides the Berkovich probe?
Yeah, I have a qubit.
Oh yeah, you have a cube corner. We talked about that one. You don't have a conospherical probe. I remember being surprised by that. So people are typically doing scratch testing with conospherical probes because they're radially symmetric, and they're larger. So you especially for friction testing, you want a really big probe. But specifically a Berkovich is a bad probe. Any triangular probe is a bad probe to test with because I have no idea, what way that probe is facing right now. You could be scratching on an edge. You could be scratching against a face. If you think about, could be scratching this way.
Yeah.
The probe could be this way. So I actually have run this test before, and you can see the directional dependence of a Berkovich probe depending on which way you're scratching.
Okay.
So that means your next Berkovich probe, it could be 30 degrees different, and all of a sudden you're getting different results. It also isn't good to blunt your Berkovich probe. So I would recommend if you want to do scratch testing, when you get to that point, let's have a discussion about applications, and what what probe you should be looking to purchase. But that's the other physical thing we should be aware of. And then earlier you had a question about what we can control in the lateral direction of these load functions. I kind of went really quick over this. You can change the max to, so one, it's just like our standard load functions. You can change anything you want. Whether it's useful is a different question. But here you have begin lateral displacement and end lateral displacement. That's for this segment. So this segment is going from 0 to -5. This segment goes from -5 to +5. That one doesn't go anywhere. It stays at +5 the entire time. So you can go through and you can update these one by one, but especially when you get to, tilt and retrace, it can be a lot to manage. So down here are your global settings that can change the scratch length. So right now the scratch length is 6 microns here. I change this max displacement 7 and the min displacement to -7. It updated these two items, and then it made this longer proportionally. So you can update the entire load function to change the length of the scratch. And then, of course, you can also change. Can you change the time? You must be able to change the time. Duration. So you can make that very long if you want to scratch slowly for some reason, if that's important for your sample, or very quickly.
Okay. Okay.
That's really all we have for scratch. I just recommend conospherical probe. Start with low forces, see what the sample does. You don't want to rub your probe off. If you have a diamond-like coating and a diamond probe and you go to a really high force, you run the risk of just wearing off the probe. So yeah, those are all the comments I really have for scratch. Are there any specific questions or things that you'd like to revisit?
No, just the use of it, I guess, is very clear.
I'm sorry, can you say that again?
No. Your training is good. So far for the procedure we discussed, I guess is fine. So one thing for the probe, I don't know. Does the probe has a warranty?
Does the probe specifically have a warranty?
Yeah.
Not typically. They're considered consumables. I mean, if it's defective
Oh,
coming out of the tube, of course, that's a whole different discussion. But once the probe is in use, uh, what you do with it is up to you. And it's the user's responsibility to keep that probe safe during testing. And they wear,
okay.
even even just doing indents, a lot of indents. I say a lot, I mean like an extreme amount of indents. You don't blunt it after 3 indents in your sample. But yeah, I mean, I have customers. You don't have any of these options, but I have a customer who has a temperature stage and they are heating a diamond-like coating and they are doing indents on it. And the probe is also diamond. And they get 8 indents per probe before it's no longer usable because they blunt it so much, because heat is so hard on diamond. So yeah, there's no warranty once it's in use. Obviously, if it's defective, that's a totally different conversation that we would have.
Yeah. So, okay. Another thing. Earlier, I guess last week you emailed Jiangxin to email me the upgrade. So I guess at the beginning we discussed about that. So for the stage. Let's say if I wanna heat or cold my sample, is
It's
that
not
I like?
That's not possible on your system. That is not currently an upgrade opportunity for the TS77.
Okay. Okay.
Yeah, no, I provided the only 2 upgrade options available to the TS77 at this time.
Okay. Sounds good.
Yeah. I'm sorry, Nico.
Yeah. I wanted to ask about the load that we can go for. Means if we are having a very hard surface that we want to scratch test, what should be in our mind before we set the load?
Caution. What we think about when we have a hard sample, diamond is very strong in the normal direction. It's not very strong in the shear direction. So actually I have that number somewhere about what that diamond strength is. And we need to be doing like a back of napkin calculation to have a rough idea of what's an appropriate number to go to. I also recommend starting low, right, instead of going high. Yeah, so we have to be thinking about the physicality of diamond and what that looks like.
So how much that force value will be? The low one, like what is right now is 1000 micronewton.
It's going to entirely depend on the sample.
Okay.
Right, scratching a soft thin film is very different than scratching a diamond-like coating.
Okay, so we are thinking about scratching a internal 718, which is very hard.
Mm-hmm.
So okay, we'll see.
I can send you. Let me. We we have an entire big discussion about this. Let me send you those details, and you can like with the way to think about it. I will. Sorry, let me just write that down quick. I will say I've only ever seen it happen really once. I mean, I'm sure customers blunt their probes all the time on hard samples, but I've really only seen one customer one time wear away a probe, and that's because they had a specialty transducer that could scratch at 10 newtons, and they did that on a diamond-like coating, and then were surprised that the probe was gone. So like that's a good example of like it's possible, but it's pretty rare. I don't know if I've ever seen it with a low load transducer. It also is going to depend on the size of the probe. Scratch testing is one of those very annoying quantitatively qualitative tests, right, where everything is calibrated and correct, but the probe to sample interaction is what matters the most. So if you have a very large probe, it's not going to be able to get as deep into the sample, right? If we think about trying to plunge a beach ball versus a ping pong ball into water, that interaction is very different. So if you have a sharper probe, a 1 micron conospherical probe, and you put a lot of force behind it, you're going to end up deeper in that sample, and there's going to be more wear on the diamond. Maybe, And then if you have a very, very large probe and you're dissipating some of that, it's possible that that wear will be very different.
Okay, thank you.
Yeah, you're welcome. Sorry, it's one of those great it depends answers, which is always difficult, but it's always fun to explore as we have specific things. I do have a note still that I wanted to look into your sample a little bit more. You gave me the material when we talked last time. Is that the same material you intend to scratch on?
Yes.
Okay. Let me do a little bit more talking to my applications department, and I'll be in contact via email with like any thoughts or ideas or recommendations we can provide from our end.
Yeah, that would be helpful. Thank you.
Yeah, you're welcome. So this was about right. Typically, scratch training takes between, an hour and a half and 2 hours, depending on how things go. So I am complete, I believe, in all the training topics that we had intended to discuss, but I do have another 15 minutes. If you guys had any questions about anything that I can assist with or that I can add to my list to follow up. Or if there was anything that was unclear during the other portions of the training that we'd like to revisit.
I think this was pretty clear. I wanted to ask about the analysis.
Yeah.
So how can we do that, and what are the options that we can see into that?
Which analysis are we discussing?
The scratch test.
So if we go back to the analysis, I mean, we're looking, you get these graphs, right? So this is corrected. I'm going to go ahead and open it uncorrected again. So these are the two that we programmed. We programmed the normal force, and we programmed the lateral displacement for that scratch. So I want to know if it said what it did, right? And it did. These followed well. So then from there, I get measurements. So I get this lateral force, and I get this normal displacement. And again, we talked about this tilt. So I want to take that out because I want to know, what happened. Because this scratch, I don't know how much of this scratch is sample tilt and how much of it is real, how much of it was actually deformation into the sample. So I'm going to go ahead and do tilt correction here to flatten that out. So if we look at this, then we can start to think about what's happening, segment by segment. It's pretty obvious here that we're tracing. We're at this normal displacement of around 0. We then load into the sample during this segment. And so we can see our normal force is increasing. Our lateral force is still at 0. Do you remember earlier when you asked about noise?
Yes.
This, I think, is a good example of how that changes, right? In this case, in this lateral force, when we're just sitting at the sample surface, we can see how there's a lot more noise in the data. And then as soon as we start to load, because we're in contact and some of that noise dampens out, this looks a lot clearer.
Yes.
Now, of course, during the scratch, this looks like noise. I don't think this is noise. I think that it's aluminum, right? And aluminum's kind of sticky and it's we get buildup sometimes. And so I'm thinking that this is actually, instead of scratching like smoothly across the sample, it's like doing this kind of. So that's what I don't think this is noise. I think that that's real. I think that that's what's actually getting measured by the probe as it's being dragged. So so we're loading, and then we can look at the hold. So here's our scratch. We're holding in the normal, and we are measuring a pretty constant lateral force. As soon as we're loaded in, we're scratching. And this might have been low enough that we actually didn't cause any plastic deformations. This might actually be a pretty good friction test, but I would have to run more before I could definitively say that. I'm sorry, I'm struggling with these bars. There we go. So yeah, there's some normal displacement here where we load in, and then as soon as we start scratching, it pops up, which is a little bit strange. What I'm thinking happened is that it loaded in, and aluminum is so plastic. I wonder if, as it tried to move, it kind of popped out of that plastic deformation hole a little bit as it performed the scratch. So it kind of popped up and out and over maybe some buildup. That's what we're seeing here. And then it kind of comes back down. Like maybe we got out of the initial indent and now we're scratching. Well, we got out of the initial indent here. I mean, it's a pretty long scratch. But I think that that's something that's happening here. So we can go through and we can physically look at what's going on. What I'm kind of curious about is this little bit. What happened here? So during the unload, our lateral force went negative. So instead of going down to the sample, it went up. So this also, it seems like it bounced up and off some buildup in the sample, right? If we're scratching and we're building up any sample, any debris, then as it's unloading, it looks like maybe it popped up and out, or maybe it was a little stuck, actually. Aluminum, like I said, is pretty sticky. And you can see this here. So this is not a great example, but sometimes I would argue that this is probably the normal displacement here at the end of the test, which is about 30 nanometers versus 0 at the beginning. So we probably scratched like a 30 nanometer scratch into the sample. That's probably what's left on the sample surface. So you can go through and you can get that kind of information, right? You can look at what happened and look at what happened at what points. Let me grab that document really quick.
I think we can try in scratch test on a quartz sample.
I would not. You can. I would not. You're going to blunt the probe. Quartz is pretty hard. It's one of those things where you're welcome to try that. It's just that you're not really looking for data right now on the fused quartz, and so you're doing really nothing but risking your probe. You know, if you put in too high of a force and we don't know what a good force is, you run the risk of causing blunting. Oh, shoot. Actually, it was, hold on, sorry. There we go. Come on. Okay. Let me reshare here. I think you might have a slightly updated version of this, but. So there's this basic nano scratch testing, setting up a scratch, goes through the tilt correction. This one's a little bit more obvious because there's not, you know, so much strangeness. So here you can see between here and here, it's flat before and after. But if we're looking at data, this is a coefficient of friction result, in which case you can get this friction plot. So that's some analysis you can do. But, you know, when you're looking at like what the scratch is actually doing, critical point of delamination is pretty common. So in this one, we have this ramping normal force, and this is the scratch. This is a different transducer, but it shows the same problem, the same behavior. And you can see here that at this point, all of a sudden your lateral force drops as your normal displacement increases. So you've broken through the sample in such a way that it usually causes some sort of bump in the lateral displacement and your lateral force as that tip punches through the sample surface. So that's some analysis that you could also do. What force does that critical point of analysis happen at is what people are typically looking for.
Yeah, this is helpful. Gives us an idea about how we can use this scratch test for our thin film.
Yes, absolutely. Okay. I'm sorry?
We are intended to do some scratch test on some thin film that we have multi-layer. So we want to see the delamination and what happens with that. So that will be helpful.
Yeah, absolutely. There's some really good papers out there too. If you read some of the, the literature out there, it's pretty helpful. Yeah, again, there's no like, aha, you have calculated the hardness modulus and therefore you are successfully done with this test. It's like, well, what did the scratch test do and what does that tell us about the sample? It's a lot more, like I said, a probe to sample interaction. I think that we have to think about a little bit more robustly than maybe just indentation. And indentation is hard enough. If you're talking to me, you're on
Kevin,
mute.
are you mute?
Sorry. Sorry. Yeah, I said I think that's all. I guess. Thank you so much for all the time you help us to go through all the basic training. I guess now we got all the training done, and it's time for us to to do the measurement. I guess that's when the question really popped up. I guess if we pop it later, we'll communicate with you through email, Laura, and also like I mentioned, we'll try to put a SOP down. So if you can help us take a look, that'll be very helpful too.
Absolutely. Anytime, just send it on over and I'll take a look.
Okay.
So yeah, I'll send a follow-up meeting or meeting. Nope, not anymore. I'll send a follow-up email. I will make sure our recording is moved over to the shared folder so that you can download that as well. Yeah, and I'll do some research with the applications department just to see if they've heard of this material or if any updates. I think I'll also send you the probe list of our default probe offerings, just so that you have a general idea of what a conospherical probe, what our standard offerings are. But that being said, keep in mind that we can make just about any custom probe that you want. So if you end up wanting a very specific test with a very specific geometry, just call me and we'll see what we can work out.
Okay. That's good to know.
Yeah. Okay. Any other questions or again, I don't disappear in the ether. I'm always here to answer questions. I just wanted to give us a chance here when we were kind of done with training. If there was anything else I could address.
So far I'm good.
Okay. All right. Then I will wish you two a wonderful rest of your day and I will talk to you soon.
You too. Thank you, Laura. I appreciate you.
Thank you.
Yeah. Thank you guys. Take care. Bye-bye.
Take care.